Welcome to the ChemDoctor, and this video goes out to all the hardworking students at the university level and in AP Chemistry who are studying acid-base equilibria, and in particular those of you who are right now confronted with the pH of buffer problems. So what I would like to do in this video is teach the viewer how to calculate the pH of a buffer solution. Now I think where we should start with this is for me to quickly define what a buffer is. So a buffer is a solution that resists changes in pH when small amounts of either H plus or OH minus are added to the solution, where the solution contains quantitative amounts of HA and A minus. Now, we're going to do two calculations basically in this video. What we're going to do first is calculate the pH of the buffer using the KB expression, and then I'm going to turn around and we're going to calculate the buffer using the Ka expression, because I think it's really important for the viewer to realize that you can solve a problem like this using either system. The main or the key thing is that you either need to be in one system or the other and not be mixing the two methods. So what we're going to do first is calculate the pH of this solution using the base reaction. So I'll go ahead and label it base reaction. All right, and this is the equilibrium where we have A minus plus H2O. All right, in equilibrium with HA plus OH minus. And in this problem, actually, they gave us the KB to start with. So the KB is the one associated with this particular equilibrium. Now, what we're going to do initially is set up our ICE table. And we see that we've been given an initial concentration of 0.19 molar of A minus and 0.57 molar of the HA. All right, and we have 0 of the OH minus to start with. So the equilibrium is going to shift to the right in order to produce some hydroxide, and in our ICE table we're going to show that this way. So it'll be 0.19 minus X. We'll have 0.57 plus X, and then the hydroxide will be X. Now, in the next step, we want to write the equilibrium expression. So we're going to have KB, and we're going to write this with no numbers in it. So we're going to have KB is equal to the HA times the OH minus divided by the concentration of the A minus. Now, since we're after the pH of this, note that first we're going to actually calculate the hydroxide solution. So once we have that, then we're going to have to do another calculation to get to the H+. So to facilitate this, though, I'm going to rearrange my equation. So we're going to have the OH minus is going to be equal to the KB times the A minus divided by the HA. All right, and now we can go ahead and plug in the numbers. Now remember, because we're dealing with a small equilibrium constant, this one's 10 to the minus fifth, we can neglect the X in the sums, which I'll show this way. And now we can go ahead and plug our values in. So we're going to have the equilibrium constant, KB, which is 2.4 times 10 to the minus fifth. All right, the A minus is 0.19, and the HA is 0.57. So my OH minus concentration calculated out is 8 times 10 to the minus 6. Now, to get to the H+, I'm going to use basically the KW expression, which is the following. So we have 1 times 10 to the minus 14th. That's the equilibrium constant for the autoionization of water at 25 degrees centigrade. It's equal to the ion product H plus times the OH minus All right, and now let's plug in our values. So we're solving for the H plus, and the OH minus 8 times 10 to the minus 6th. So solving this out, my H plus is going to be equal to 1.25 times 10 to the minus 9th. Remember, to find the pH is going to be equal to minus the log, and then we insert the concentration of the hydronium. So the pH of this buffer is equal to 8.9. All right, and let me just highlight that. I'm going to circle it here. Now, as I promised, what I want to prove to the viewer is that we can actually use the HA expression to solve the same exact problem. So what I'm going to do is turn this on its head, and I'm going to write the acid expression now over here. So in that case, we're going to have the HA plus H2O in equilibrium with H3O plus A minus. All right, now we need the Ka for this expression. You cannot use the Kb here. All right, so we need to find that. And the way we're going to do it is use the Kw expression. So we're going to have 1 times 10 to the minus 14th, which is equal to the Kb, 2.4, times 10 to the minus 5th, times the Ka. So the Ka for this solving is going to be 4.2 times 10 to the minus 10th. Now, you set up your ICE table exactly the same way, but note that the ratio now is going to be different. So initially we're going to have 0.57 of molar of the HA. We're going to have 0.19 molar of the A minus and 0 of the H3O plus. So when an equilibrium is attained, right, Le Chatelier's principle, we have to shift to the right to make some hydronium. So it would be 0.57 minus X for the hydronium, and 0.19 plus X. Now, let's go ahead and solve for the Ka expression. I'm going to do it with no numbers first. So Ka is going to be equal to concentration H3O plus times the A minus divided by the HA. All right, now I'm going to do the same thing I did in the last problem. I'm going to go ahead and solve for the H3O plus. All right, so let's go ahead and do that. It's going to be H3O plus is going to equal my Ka times my HA over my A minus. Now you'll notice in this diagram that my ratio switched, right? Look over here. See, our ratio here is A minus over HA. Now in the Ka expression, it's going to be HA over A minus. Now I can go ahead and plug my numbers in. So we're going to have 4.2 times 10 to the minus 10th. All right, and then my HA is going to be 0.57. Again, we're neglecting the X. All right, and then this is going to all be over 0.19. So my H3O plus concentration is going to be 1.26, which is very close to the other value, to the minus 9th. My pH is going to equal minus the log, plugging in 1.26 times 10 to the minus 9th, all right, where my pH then is 8.9. So we end up with exactly the same value calculated with the other equilibrium expression. Alright, and what I'd like to do with that is go ahead and close the video. I'd like to thank the viewer for coming to ChemDoctor and watching my presentation. You can find more videos at www.chemdoctor.org. Thanks again for watching.